Okay, you guys, let's do a little recap of what we did today. So first of all, we did this interesting game with the coins, and I'm going to go straight to that one so you guys can see it. We're moving coins. So we started with 3 coins. Actually, we started with 1 coin, then we went to 2, then we went to 3. We talked about how many moves you can make. So for instance, we started with a quarter, and a nickel, and a dime. And so that's 3 coins, and how many moves does it take before you can get back to this, okay? So I did 1 move, 2 moves, then I can go, I want to get back to where it was, and I can go 3 moves, 4 moves, 5 moves, 6, 7 moves, okay? So we did 2 coins, and it takes 1, 2, 3 moves. So, and if you move just 1 coin, it's just 1. So we filled out our pattern. We got number of moves, number of coins, but then we were like, what happens if you got 4? Well, 4 turned out to have 15 moves. It was really difficult. 4 was like quarter, nickel, penny, dime. And then it took 15 moves to get that to work. And then we thought, we got to get a pattern because this is going to drive me crazy. So what we saw is a pattern here. Our pattern was just we added 2, then we added 4, we added 8, added 16. Those are like doubling. So we came up with a formula that worked for our coins. So we did a recursive formula for our coins. We came up with a recursive formula showing, let me squeeze this under here, a of n equals 2 times 8 to the n minus 1 plus 1. So if you put in 7, double 7 is 14, add 1, you get 15. So if you had 5 coins, you'd put 15 in here. 2 times 15 is 30. Plus 1 is 31, and then it keeps going. So it worked out pretty well, that particular formula. And then filled up our chart. Using that, we got 1 coin, 2 coins, 3 moves, 3 coins, 7 moves, 4 coins, 15 coins, and then 5 coins took 31 moves. Okay. We also looked at it as a geometric sequence, but the explicit formula. So if I plug in 1, I'd have 2 times 1 is, if I plug in 2 to the 1, minus 1, it gives me 1. I plug in 2 to the 2 minus 1 is 4, minus 1 is 3. If I plug in 3, I've got 2 to the 3rd power minus 1, that's 8. Minus 1 is 7. I go 2 to the 4th, well that's 16. Minus 1 gives me 15. So that is a good explicit formula, okay? Then we graphed it, and it looked exponential is what I expected to do, okay? So then this formula could work for any number of disks, but then we didn't want to do that many disks, okay? So then we also talked about formulas. Let me real quickly get my notes on our formulas. So what we did on our formulas, we realized we were having a difficult time with our formulas, and we talked about this. If you're going to make a formula, you need variables. This would be variables. So we have 2 types of formulas, arithmetic and geometric. We know arithmetic is where you add or subtract the same thing each time. Geometric is where you multiply the same thing each time. So again, between arithmetic and geometric, we turned out that we have a recursive formulas and explicit formulas. Recursive formulas are a little bit different. You have to have the first term, and then you have to have this a to the n minus 1, which means the previous term. So I went through and I circled everything that has to stay a variable. So when you make a formula, these are my variables. I also have a recursive formula for my geometric. I have to have the first term. I've got to go g of n equals g to the n minus 1 times r. And I circled everything that has to stay a variable when you make a formula. We also have explicit formulas. We've got a of n equals a1 plus n minus 1 times d, and g of n equals g1 times r to the n minus 1. So I did a couple of examples. I'll do these quickly so you can see it. I'll do it real quick on my board here. Get myself all situated here. Hopefully you can see my notes. Yeah, you can. Okay, so first example I did was this. Let's just say we have this formula example. 3, let's go 6. No, I don't want to do that one. Let's do a different one. Example, I don't want to do that one. Let's go 3, 7, 11, 15, dot, 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 dot. Okay, we know it's arithmetic because we're adding 4 each time. If I needed the recursive I go here, I'm going to say A1 equals 3. There's my variable. Okay, I'm going to say AN equals A to the n minus 1, and D is 4, plus 4. That is my recursive formula. If I wanted to make an explicit formula out of this, I would go, here it is, I'd go explicit, I'd write that down. I would write AN equals A1, which is the first term, which is 3, plus my n minus 1, and my D is 4. There's my formula. That's all I need. Okay. Then we talked about if it's geometric. I'll give you another example. Shift this over. If I had something like this, 3, 6, 12, 24, dot, dot, dot. I know that's geometric. And since it's geometric, if I want explicit, nope, let's do recursive first. Recursive, I would use these formulas right here. I'd write down g of 1, which is the first term, which is 3. Then I'd write g of n is equal to g of n minus 1 times my r, my multiplier is 2. There's my recursive formula. That's all I have to do. If I want my explicit formula, here it is. I start with g of n equals g1, which I know is 3. R is my multiplier, which is 2 to the n minus 1 power. That's my formula. That's all I need, okay? So if you don't have these notes, every place I have highlighted in pink stays a variable, okay? That's all I have. We're going to practice again tomorrow, okay?